Okay, we have 2 sections today, but we already know how to do most of the stuff in these 2, or we've already gone over it anyway. You may not feel like you know it just yet, but we've already gone over a lot of what's going on in these 2 sections. Anybody have anything we need to talk about before we get going? I didn't give Tess back in here yet, did I? I'm sorry, I forgot them. I'll bring them Thursday. Okay. I just forgot I hadn't gave those to you yet. Okay. Then that should be everything. Okay. All right, so 10.3, we are doing something really similar to what we did last time. Okay, we're doing a hypothesis test for means again, but this time we're getting rid of our assumption that we know the population standard deviation. Okay? So we're in a sigma unknown situation. Okay? And what that's going to mean for us, just like with confidence intervals, when we get away from knowing the population standard deviation, we're going to use a t test statistic, okay? Like we used a t critical value with confidence intervals. Let me adjust my pen here. It's a little skinny for some reason. So if we're going to use t instead of z here, we have a couple of adjustments we have to make. The first thing we need to adjust is we need to adjust our formula for a test statistic. Okay. So here's our formula I'll be using today. Will give us a t test statistic instead of a z. And the only thing that looks any different at all, okay, is the part where we have t instead of z. And in the actual formula, instead of sigma, population standard deviation, we have S, which is our standard deviation from our sample data. Okay. So that part's not a big deal. We're just switching labels. Okay. I know we're doing. We still need a sample size of at least 30 to know our distribution is approximately normal. It's just that we're in the situation where we don't know the population standard deviation, so we use T instead. Okay. The place where more of an adjustment is going to come into play for us is when we go to make our conclusion at the end of a hypothesis test. So if you think back, it might seem like a long time ago. It kind of seems like a long time to me since we talked about 10.2. The way we made our conclusion at the end of a hypothesis test is that we would get our test statistic, find the p-value of our test statistic, and then compare that p-value to our significance level alpha. Okay. Unfortunately, we're not going to be able to do it that way in class. I mean, you can use software and get a p-value for a t test statistic, but with the tools that we all have available to us, the only information we have are the t-values that are on table C. So that's not going to be enough information about the t-distributions for us to come up with a p-value. We're going to p-values the area under the curve and all that, and we don't have that for t's. Okay? So what we're going to do is we're going to use a little bit of a different strategy. It's just a different way of thinking about the same thing. So I told you we had 2 methods we would use for coming up with conclusion. So p-values were one way, and then today we're going to use something called a rejection region. And use rejection region. I got a little bit ahead of myself here. What's it doing now? Slides are acting weird. Okay. With T's, degrees of freedom, I got that reminder there, degrees of freedom are n-1. Luckily, that's the same as we had when we were doing confidence intervals, so Hopefully that's familiar. Okay, so what we're going to do instead of finding a p-value is we're going to use these things called rejection regions. Okay? So let's look at a slide that gives us the rules on the rejection regions, and then let's talk our way through these. Okay, you don't necessarily have to remember a rule for rejection regions. Okay? So this first one says if we're doing a left-tailed test, it tells us when to reject the null hypothesis. Okay, so if we're doing a left-tailed test, so the t that it gives us over on the left side is our test statistic that we calculate with our formula. Okay, and then these t sub alphas, or in the two-tailed case, t sub alpha over 2, that's just a critical t value. Okay? So what's going on is we're going to split our curve into two pieces. Okay? So we'll have a line down our curve somewhere. If our test statistic falls on one side of that line, we fail to reject the null hypothesis. If our test statistic falls on the other side of that line, we reject the null hypothesis. And the way that we decide where that dividing line belongs, okay, is by looking up a critical t value. Okay? And that's not difficult. That's just using our degrees of freedom and our significance level to come up with this critical t. Okay? So what the first one's telling us here is that if our test statistic is to the left of our critical t on a left-tailed test, we reject the null hypothesis. If our test statistic is to the right, greater than our critical value for a right-tailed test, we reject the null hypothesis. Or if it's to the left of the negative or to the right of the positive for a two-tailed test. And so let's think about the picture of what's going on. And then you won't even, if you get the idea of what we're actually doing, you won't have to remember the rules. Okay? So if we have a left-tailed test, okay? We have a left-tailed test. We have some critical t over here. Pen's going to give me trouble today. Okay. So we've got some critical t over on the left side because we're doing a left-tailed test. And what the rule says is that if our test statistic falls in this left tail, we reject the null hypothesis. Okay. So this area over here on the left side, that's our rejection region for a left-tailed test. Okay. If we're doing a right-tailed test, I don't know why this thing's being so crazy. In a right-tailed test, same thing, it's just the other direction. We're going to have a t over on the right side. If our test statistic falls to the right of that critical t value, we reject the null hypothesis. And if we have a two-tailed test, we'll have two t's. And if our test statistic is in either tail, we'll reject the null hypothesis, so that's two-tailed. So the only thing we need to be able to do, okay, that part we're just looking at where a number falls on the number line, really. Okay. The only thing we need to be able to do, we need to be able to come up with what these critical t values are. Okay. That way we'll know if our test statistic's on one side or the other of these. And we can do that. All we need degrees of freedom, okay, n minus 1. And then we need to know what area we want in our tail or tails. And if you remember our picture we made, right, we said confidence is area in the middle of the curve, or the stuff that's left over in the tails, that's called significance, okay, or alpha. So here we just need an area in the tails that's the same as our significance level. Okay. So let's, I think I'm talking too much on that. Let's look at one. Okay. Here, we can already find a critical t, is what I'm telling you. Okay. And it says find the critical t value that corresponds with 14 degrees of freedom at the 0.025 level of significance for a right-tailed hypothesis test. Okay, so this one's giving us degrees of freedom. We don't have to subtract. And it tells us the area, that's the same as our significance. So we need an area of 0.025. And where do we want that area of 0.025 to be? We look at what type of hypothesis test we're doing. We're doing a right-tailed hypothesis test, so we want our area to be in one tail. Okay. And we want it to be on the right side, so our critical T is going to be positive. So let's look at table C. We want 14 degrees of freedom. Want an area in one tail, 0.025, so that's the middle column, 14 degrees of freedom. So here our critical T, if this thing will work with me here, our critical T, okay, what do you find? Yeah, 2.145. So all we're doing, I want 0.025 in one tail, because it's right-tailed, one tail, 14 degrees of freedom. So our critical T is 2.145. So if we were actually doing the hypothesis test here, okay, our picture, let me move this out of the way. Okay. Our picture oh goodness. Here. We're doing a right-tailed test, so we would have 2.145. Okay. And if our test statistic falls to the right of that, this area, we would reject the null hypothesis. If our test statistic fell on the other side, we would fail to reject the null hypothesis. And how do we know which side it's on? Just we would look at our number that we calculated. Okay? So like if we had 1.5, that's somewhere over here, we would fail to reject the null hypothesis. If we had 3.1 or something like that for our test statistic, that's over here, so we would reject the null hypothesis. If you get the idea down, these are actually easier to think through than p-values. So we just put our critical T on there. And since it's right-tailed, anything to the right of that's our rejection region. Okay. If it was left-tailed, anything to the left of our critical value would be our rejection region. If it's two-tailed, we have plus and minus. We have to worry about. Got them already. Very good. Anybody else need tables? Okay, good deal. All right. How's your week starting out? I feel a weird vibe in here. I don't know. It might just be me, but we going okay? So. Did you eat a lot of candy this weekend? Not what you're interested in? Everybody still sleepy from the weekend? All right, so we can do this. Okay, we can do this. So let's do a hypothesis test. Okay, we're ready. Okay. So only new thing here, okay, we have a slightly different formula for test statistic. So we're going to get a T instead of a Z when we do our calculation. And then when we get down to the part where we're deciding whether to reject or fail to reject the null hypothesis, we'll have to look up a critical T value and then figure out if we reject or fail to reject based on that. It's the only thing new in this section. So let's do one. Okay? And it's a good refresher on the other steps in the process. Okay? Hang in there while I read this one to you. I got a book here. Okay? It says, nurses in a large teaching hospital have complained for many years that they are overworked and understaffed. The consensus among the nursing staff is that the mean number of patients per nurse each shift is 8. The hospital administrators claim that the mean is lower than 8. Prove their point to the nursing staff. The administrators gather information from a simple random sample of 19 nurses' shifts. The sample mean is 7.5 patients per nurse with a standard deviation of 1.1 patients per nurse. Test the administrator's claim using an alpha significance level of 0.025 and assume that the number of patients per nurse has a normal distribution. So a lot of information there, and let's break it down piece by piece. One thing that may have caught your eye, may not have, but may have caught your eye, that our sample size is only 19. Normally we say we want a sample of at least 30, but we're okay in this situation because it says assume patients per nurse has a normal distribution. Okay, so we can still go ahead. So we want to figure out what claim we're testing, right? We want to get our alternative hypothesis. So it tells us test the administrator's claim. So if we go back some, it says the administrator's claim that the mean is lower than 8. So that's going to be our alternative hypothesis. That will get us started. So step 1 here, we'll have our alternative hypothesis that if I can get this to work, that the mean is lower than 8. So mu is less than 8. And our null hypothesis will be that mu is 8. I mean that the mean is 8. I said the mu is 8. Good night. Okay. Step 2, now we do have a little bit more to do on step 2. Step 2, we have to think about, are we using Z or are we using T for our test statistics? So on these, one moment here. If I can. On these, we are still dealing with the mean. So, but the difference, why it's not Z, why it's T, is that we don't know population standard deviation. Okay? And the problem, the standard deviation it gives us, okay, it says the sample mean is 7.5 with a standard deviation of 1.1 patients per nurse. That's coming from our sample data. Okay? If it doesn't say population standard deviation, that means it's giving you sample standard deviation instead, S. Okay? So we are in a sigma unknown situation. We don't know the population standard deviation, so sigma is unknown. So we will use T. And we also want to state our significance level here. It just gives it to us. Our significance alpha 0.025, so we'll take note of that. It's going to drive me crazy today. Any questions so far? Okay, step 3 is where we get something a little new. We have a new formula. Slightly. We say we're going to use T. Our formula is x bar minus mu over, this time we have S, or sample standard deviation, divided by the square root of n. And mathematically, that's just going to look the same. Okay. But it's important we know what kind of numbers we're working with. We're going to get a T. All right, so let's see if you remember from last time. One of these we already know what to use. One of these is set up by our hypotheses. Which one can we already plug in for? mu, yeah, mu every time is going to come from our hypotheses. So mu, we're going to use 8. No, lost a decimal there. We're going to use 8 for mu. So we have something minus 8. Come on now. And then the other 3 numbers we get from our sample data. Go back to our problem. All right, we can skip past the 8. We've already used it. That was our mu. Then we have a simple random sample of 19 nurses shifts. So our sample size n. Says the sample mean is 7.5 patients. That's x bar. And standard deviation here is S. If it doesn't say population standard deviation, it's going to be S, sample standard deviation. Now we can plug in 7.5 minus 8. You ever just have one of those really frustrating days? 7.5 minus 8. S is 1.1. Maybe. Come on now. You'll get there before I will today. Divided by the square root of the sample size, which is 19. Since we are calculating a t-value, we're going to leave 3 decimal places because we have 3 decimal places in our t-table. Okay. Let's see what we get here. And so I get negative 1.981. Anybody else try and get that same number? You just trusted me? That's dangerous. I think that's right. Okay, so last step, we need to make our conclusion. No p-value involved here. Okay. What we're going to use instead, we need to come up with a critical t to figure out where our rejection region is. So to do that, we need to go back and get some information. Okay. One thing we need is we need to see that this is a left-tailed test. And we have a less than symbol in our alternative. That's left-tailed. Goodness. Okay. The other thing we need to know, we need to look back at our alpha, our significance level. That's going to be the area we want in the left tail for our critical t. Okay. And then the only other thing we need to know degrees of freedom. Our sample size was 19, so we'll have 19 minus 1 degrees of freedom. So our critical t, let's go to our table. So we want, oops, sorry. Well, 0.025 in one tail, left-tailed, so we're going to have a negative t. We got to remember that part. So 0.025 in one tail, that's the middle column, 18 degrees of freedom. And again, it's left-tailed, so we have to make it negative. So our critical t here will be negative 2.101. Okay. Since it's left-tailed, okay, I always like to make a sketch. Okay, you don't technically have to make a sketch to come up with a conclusion. Okay? Since it's left-tailed, what we would do is we would reject the null hypothesis if this number is to the left of this number, and because it's a left-tailed test. In this case, it's not, so we would fail to reject the null. I like making a sketch. Okay? I like having a little picture. So my critical t over here, negative 2.101 somewhere. Here's my rejection region. So from here to the left, because it's left-tailed, we will reject. If our test statistic is over here somewhere, we'll fail to reject. And this number, right, that's closer to 0 than negative 2.101, right? So it's going to be on the right side. So here, oh no, this number like over here somewhere, right? That's exaggerated, but it's on that side. So we fail to reject the null hypothesis. Come on. They're having to order another pen tip, if you wondered why I'm just suffering through up here. Failed to reject the null hypothesis. If our number had been like negative 2.5 something, it would have been on the other side of our critical value. So it would have been in the rejection region, so we would have rejected the null hypothesis. This is the same idea as p-values, we're just executing it differently. And because with a p-value, what we're doing is we would say, what's the area to the left of this thing? If the area to the left of this thing is smaller than the area to the left of this number, we reject. You know? So that's the same thing as saying it's on the left side. Same idea, we're thinking about it differently. Instead of thinking about the area under the curve, we're just thinking about the t-values and comparing those instead of comparing the areas. Same idea though. Questions on any part of that? Can't think of anything? Let's do another one. We won't go quite as slow through it, okay, but let's do another one. That's all there is in 10.3. Okay? We just had those slight adjustments. Let's look at this one. Time we've got department stores chosen marketing strategies for many years under the assumption that the mean amount spent by each shopper in the store is $100. The newly hired store manager claims that the current mean is higher and wants to change the marketing scheme accordingly. A group of 27 shoppers is chosen at random and found to have spent a mean of $104.93 with a standard deviation of $9.07. Assume that the population distribution of amounts spent is approximately normal and test the store manager's claim at the 0.05 level of significance. Okay. So we want to test the manager's claim. The manager's claim here is that the mean is higher than $100, so greater than $100. That's our alternative hypothesis. Our null hypothesis would be that mu is equal to $100. It's $100. Step 2. Okay, same reasoning as before when we're using t, but let's look at it. Okay. Again, we're working with means. And we are not given the population standard deviation. Okay? When it talks about standard deviation, it just says standard deviation, so it's talking about standard deviation of the sample. And again, I will make it very clear from test time. And on the last test, I said sigma is unknown. And so we're in a sigma unknown situation here. And so we're going to use t. Okay? So we're dealing with means. Sigma is unknown. We're going to use t test statistic. And we want the significance level. So it says at the very bottom, test the claim at the 0.05 level of significance. So here for alpha, we're using 0.05. We're ready to do our formula, get our test statistic. So in our formula, we already know mu, it's going to be 100. Okay. Put the decimal place there if I can get it to work. We need x bar sample mean, s sample standard deviation, and n sample size. So as we're scrolling through, it had a group of 27 shoppers. That's our sample size. Had a mean of 104.93. That's x bar. The standard deviation of $9.07. That's s because it doesn't say population standard deviation. It's just sample standard deviation. Okay. So now we can plug the rest of the numbers into our formula. So 104.93 goes in the top, and then we have $9.07 divided by square root of 27 bottom. Use 3 decimal places here. Here I get 2.824. My test statistic, I think. Okay. So since we're dealing with t, the last thing we need to figure out our critical t so we can make our conclusion. So this is a right-tailed test. We have a greater than symbol. In our alternative hypothesis, we want an area of 0.05 in the right tail, so 0.05 in one tail. For degrees of freedom, we have 27 minus 1, so 26 degrees of freedom. So go to table C. Not a good technology day. 26 degrees of freedom, 0.05, and one tail in the right tail specifically. So 0.05 and one tail is the second column. 26 degrees of freedom. You get 1.706. Give me just a second to see if I can unfreeze this thing now. Sometimes if I flip it and then flip it back, it'll behave. Is it working now? Yeah. All right, so critical T, 1.706. We don't have to make it negative because it's right-tailed. So that's our critical T. And I like to make a sketch. You don't have to. You could just compare the two numbers, and since it's right-tailed, we will reject the null hypothesis if our test statistic is to the right of this number. It is. This is bigger than our critical value of T, so we're going to reject the null hypothesis. But I like making the little sketch. Here it's right-tailed, so I have 1.706 over here. Anything to the right of that, since it's right-tailed, is going to be my rejection region. Okay. And my test statistic does fall to the right of that, somewhere over here. So we reject the null hypothesis. If I could get this to right. You got that there. Direct HO. Sorry, it's so ugly. Okay, somebody asked something. Anybody got a question? Quiet bunch today. Hey. One more, because we need to do a two-tailed. Right? We need to do two-tailed with the rejection regions. Let's look at one more of these, and we'll go to the next section. How we're doing on time? We're good. All right, this one, we got a meat packing department. They normally put their beef into 2-pound portions. Supervisors are concerned the machine's no longer packaging the beef to the required specifications. To test the claim that the mean weight of ground beef portions is not 2 pounds, the supervisors calculate the mean weight for a simple random sample of 20 packages of beef. The sample mean is 2.10 pounds with a standard deviation of 0.33 pounds. Is there sufficient evidence at the 0.01 level of significance to show that the machine is not working properly? Assuming the weights are normally distributed. Right. So the claim we want to test here is that the machine's not working properly. So if it's not working properly, that would mean that the mean weight is not 2 pounds, because that's what it's supposed to be. It doesn't say more. It doesn't say less. We just want to test to see if it's not 2 pounds. Okay. So what's our alternative hypothesis going to be? That the mean is what? Not greater than, not less than, not equal to, yeah. Our null hypothesis, that the mean is equal to 2. And then it's an equal sign there. It's just got a extra line. So if it's not working correctly, that would mean that the packages are not 2 pounds, not equal to. Okay. All right, I won't bore you with our justification here. The main thing is sigma unknown, just like the others. So we're going to use T. Okay. And for alpha, our significance level, is here we want to know is there sufficient evidence at the 0.01 level. So alpha this time will be 0.01. Okay. When we go to plug into our formula for mu, we're going to use 2. That's what we're assuming to be true. So in our formula, we'll have something minus 2. So as our sample mean minus 2, so we want there. And then divided by S over square root of n. So going back to our problem, we have a sample of 20 packages of beef, so that's our sample size, n. Sample mean is 2.1, 6 bar. Sample standard deviation, S, is 0.33 pounds. Okay. We have 2.10 minus 2 over, what was it? Make sure I get them right for you. 0.33 divided by the square root of 20. And 3 decimal places here. Okay, here I get 1.355. Okay. Our test statistic. We want to make a conclusion. Since we're dealing with T, we need to figure out our critical value of T. So we're doing a two-tailed test. Best I can do there. Two-tailed, alphas 0.01. So this time we're looking for an area of 0.01 in two tails because it's a two-tailed test. And our degrees of freedom be 19. 20 minus 1. So 19 degrees of freedom. 0.01 in two tails. That is the fifth column. 19 degrees of freedom. 2.861. Come on now. So, especially on two-tailed, it's helpful to make a picture, okay? Because since it's two-tailed, not only do we care about 2.861, we also care about negative 2.861. Okay, so we have one on each side. Here we have negative 2.861. Here we have positive 2.861. If it's in either one of these tails, we will reject the null hypothesis. But in this case, 1.355 is like somewhere over here. So what's our conclusion? We failed to reject. Yeah, so if it was in one of the tails, we would reject. But since it's in here in the middle somewhere, we failed to reject the null hypothesis. Questions on that one? Can't think of anything? All right. Since I'm having so much trouble with the pen, we'll just stop there today. And we'll do 10-4 Thursday. And we'll figure out what to do, how to rearrange after that. Okay. No big deal. We're on a good schedule. We don't have to rush through anything. So. All right. If you didn't get in on the sign-in sheet, make sure you get on there before you leave. It's be floating around somewhere. If you have any questions or anything, I'm up here.